When you have several uneven pools of tokens, the most direct way to make them equal isn't to guess individual exchanges. Instead, you scoop them all up into one giant pile. From there, you take that single aggregated pile and deal it back out into 3 perfectly identical portions. We can apply this logic to the problem at hand. We have 3 people. Person A starts with 50 rupees, person B has 100, and person C has 150. We need to find how much money B and C together should give to A so that everyone ends up with the exact same amount. Our options are 15, 25, 50, or 75. Tracking each individual exchange between these 3 people involves several moving parts. To find the answer more efficiently, we can look at the entire group as a single closed system. In this system, we rely on the conservation of money. No matter how many rupees we move between these 3 people, the total amount of wealth held by the group remains the same. The first step is to find that total. By adding 50, 100, and 150, we see the total pool for the group is 300 rupees. To find what an equal share looks like, we take that 300 and divide it by the 3 participants. This gives us our target. For everyone to be equal, each person must end up with exactly 100 rupees. This 100 rupee target establishes exactly where every account needs to finish. With this finish line in place, we can now calculate the specific transfers needed to reach it. Take a moment to look at person A's numbers. Based on where they start and where they need to finish, how much money does person A need to receive? We can see the gap clearly on this progress bar. Person A starts at 50, but they need to reach the 100 rupee mark. To bridge that distance, person A requires an additional 50 rupees. The prompt asks how much B and C should give together. This means we can treat the donors as a single unit. As this arrow shows, the specific breakdown of who gives what doesn't change the fact that 50 rupees must enter person A's account to reach the goal. Focusing on the recipient's deficit provides the answer directly. Calculating how much B gives versus how much C gives becomes an unnecessary step. Comparing to the options provided, option C, 50, is correct. We prove this by simulating a simple transfer. If person C gives 50 rupees directly to person A, C drops to 100, A rises to 100, and B stays at 100. Everyone is equal. This visual check confirms that calculating the end state average is a reliable way to solve redistribution problems without needing to trial and error different exchanges. This 3-step algorithm works for any group. Step 1, add starting values to find the total pool. Step 2, divide the total by participants to find the target share. Step 3, subtract the recipient's starting amount from the target to find the transfer needed. Looking at the system-wide average provides a consistent path to the answer. It replaces the need to balance individual accounts with a direct 3-step process.